The discrete Fourier transform is fundamental to many questions in science and technology, and naturally we want to be able to compute the discrete Fourier transform fast. And the classical way to do that is the so-called FFT algorithm. So the FFT algorithm, which is the Fast Fourier Transform algorithm, was first designed in 1965 by Cooley and Tukey. So it's also known as a Cooley and Tukey algorithm, and has led to a revolution in digital signal processing.
This is Michael Kapralov, an assistant professor of the IT school at EPFL, and indeed, the Fourier transform is central to our information age. As a result, performing the Fourier transform in a fast and efficient manner has been one of the greatest breakthroughs of computer science. Professor Gilbert Strang of MIT described the Fast Fourier transform as the most important numerical algorithm of our lifetime. But why is the Fourier transform so central to our modern world?
This transform is really fundamental to numerous areas of science and technology. You can think of signal processing, data analysis, medical imaging, and perhaps the very well-known example is image and video compression schemes. So think of JPEG.
You do know what JPEG is, don't you? What about MP3? These are digital formats for images and sounds, and there are plenty of other formats for videos as well, like H.264, which is the one I'm using for this video. Such audiovisual files are opened by each and every one of us every day, and every time you're looking at a digital picture, every time you're listening to digital music, and every time you're playing a digital video, some FFT algorithm will be running in the background. As Richard Braniuk, a professor of Rice University, puts it, FFTs are run billions of times a day. But how does the Fourier transform help with audiovisual compression?
In many applications, we acquire signals in some continuous domain. But these signals are usually sampled at discrete intervals. We have analog to digital converters. So once the signal is digitized or sampled, the question becomes, can we compute the discrete Fourier transform of that signal?
This is by opposition to the classical continuous Fourier transform that was studied by French mathematician Joseph Fourier and others in the early 1800s. These days, we rather focus on digital data, and therefore we rather care about the discrete Fourier transform. Now,
if we are trying to compress an image using the JPEG method, what we would like to do is just say, I take an image, I take the Fourier transform of that image, and then it turns out that for most images, because these images are smooth in time domain, the Fourier domain representation is fairly compact. So we just truncate to the top few coefficients in magnitude, zero out the rest, and hence we achieve compression.
Let's explain a bit more. Signals like images and sounds can be regarded as one way of representing some fundamental mathematical objects. The Fourier transform allows us to look at these fundamental mathematical objects through a different angle. Thereby, objects that look awfully complicated in the signal domain can suddenly appear amazingly simple and easy to describe in the Fourier domain. This will be the case when the signal in the Fourier domain is mostly zeros, in which case we don't even need to record the zero values. We can just store in memory the non-zero values, which means that we'll need less memory space to record our signal. But why would the Fourier representation of images and sound be so nice and compact in the Fourier domain?
So if we think of a k-sparse signal in Fourier domain, well, this is a signal that is basically a sum of a small number of pure harmonics, plus maybe some amounts of noise.
And in music, it's pretty clear why most music are made of only a handful of pure harmonics. After all, that's how music partitions are written. Each height of a musical note imposes a particular pitch, which corresponds to a pure harmonics. In fact, there's even more than that, as, depending on instruments, each note is accompanied with a tone which is usually itself a combination of a handful of pure harmonics. However, it might be less clear why images are also made of a handful of pure harmonics. The way JPEG actually works is by first decomposing an overall image into tiny squares. Now, if the resolution of the large image is quite high, Each tiny square will likely be smooth and nearly homogeneous, which means that the frequency representation of such tiny squares will mostly be made of low frequencies. In both cases, it turns out that most of the signals is actually a composition of a handful of frequencies. Now, the other frequencies, they are usually not exactly zero because there's always some noise. But as long as this noise, these amplitudes of the other frequencies are low and negligible compared to the main signal, you can basically just get rid of them, just cancel them out, without really affecting the quality of the image or the sound.
So the underlying idea of JPEG is that we take a time domain representation, which is the image itself, we take the Fourier transform of that, and then it turns out that if we just keep the top few coefficients and throw away the rest, the image almost doesn't change. And hence we achieve compression.
This approach has strong resemblance with machine learning algorithms like PCA or SVD, or like the word vector representation we discussed with Martin Jaggi.
This is one reason why the discrete Fourier transform is important, because for natural signals that arise in applications, it sort of concentrates their energy in a small number of coefficients. And hence, just focusing on these coefficients results in savings. Savings in storage, savings in time, etc., etc. And the Fourier basis turns out to also be convenient for other reasons. And one of these reasons is the fact that convolution, the operation of convolving two signals, becomes very easy to perform in the Fourier domain.
Wait, what's a convolution and why does it matter?
So here's one reason for computing convolutions. Suppose that I have a signal x and some template signal y. And I know that a signal x is basically a shift, or maybe a shift of the signal y in time domain, plus perhaps with some noise added. And what I want is to find out what is the right shift, basically that aligns x and y optimally. One way to do it is exactly to compute a convolution. So what is a convolution? Convolution is the following operation. Well, we take the signal x, and then we consider all the possible shifts of the other signal y, and we do the dot product of x and the shifted version of y. We basically overlay x with a shifted version of y and check how similar they are.
But why would we ever want to search for the optimal translation of x that best align with y?
And this is actually the operation that GPS devices do. When they're receiving a GPS signal, think of it as x, perhaps it's a noisy version of some template signal y.
Yes, because to locate yourself using GPS, you need to measure very precisely the communication delay from the satellite to your phone. To do so, the satellite will send you a signal Y, and you know that it will look like some template X, and measuring the arrival time of Y will then boil down to determining the time translate of X that best matches the signal Y.
And now the question is, can you find the right shift? Now, if you think of doing this in the direct brute force way, if my signal x is of length n, my signal y is of length n, then I need to try all the n shifts. On the other hand, if I can switch to the Fourier domain, it turns out that all that I need to do is take the Fourier transform of x, Fourier transform of y, and multiply them pointwise. And then do the Fourier transform back. Then, in the resulting signal, if I look at the peak, at the maximum, this is the right shift. So multiplication is very easy, convolution is very important. So if we have a way of quickly switching from time domain representation to frequency domain representation, then we can take x and y, compute the Fourier transform, multiply them, compute the Fourier transform back, and we have the convolution of x and y. So this is a fast algorithm for performing convolutions.
So the Fourier transform is a key algorithm to determine optimal time translation.
Exactly. So this is a very efficient way of resolving optimal translations of one signal that make it similar to another signal.
More generally, whenever signals have a lot of time or spatial translation symmetries, then convolution and the Fourier transform will be powerful tools to efficiently deal with such symmetries. In fact, inspired by the architecture of a brain, researchers in deep learning have exploited convolution to improve the image processing of their neural networks. This has led to so-called convolutional neural networks, as well as key breakthroughs in object detection and face recognition. So yes, the Fourier transform is a big deal.
But in fact, there are also, also other reasons. Let me mention one to you, and this is something that comes up in medical imaging. For example, when one is performing an MRI scan, one can view this process as follows. So there's this object being scanned, the patient, and essentially the process of performing an MRI scan is this. We can think of the patient as a signal in time domain. So now the MRI machine basically measures Fourier coefficients of the signal x at various locations. So now the question becomes, if I want to scan a signal x or a patient, then this is basically the question of reconstructing x from a small number of Fourier measurements. So this is yet another application where the Fourier transform comes up for completely different reasons. It's just this is given by the physics of the process.
And in fact, this is not so different from what our ears do at any point in time. Our ears are made of tiny hair, each of which can only vibrate at a very specific frequency. Now, because of a physical phenomenon called resonance, our hair will vibrate if and only if it hears the pure harmonics associated with its intrinsic frequency. And when you think about it, this means that our brains are only told about the frequencies of the sound that our ears hear. Yet our brains are able to combine these frequencies to reconstitute the sound that our ears hear. Our brains apply the Fourier transform all the time. So in a nutshell, the Fourier transform has a lot of applications. We've barely scratched the surface in this video. And because of it, the Fast Fourier Transform by Cooley and Turkey has conquered the world. But what if I were to tell you that Cooley and Turkey's algorithm has recently been outperformed? Well, this is what we shall discuss next time.
That's where the Fourier transform comes in. It comes up with a way to estimate the functions on the whole real line using complex exponentials.
This algorithm runs in time about log squared n, so it doesn't even look at the entire signal.